Welcome. Today we will discuss factorial experiments. Factorial experiments. The word factorials is used when you go for experiment with several factors, each having more than one labels. For example, assume there are two factors A and B, A with two labels and B with two labels. Pictorially we can represent like this: factor A with label 1 and label 2, factor B label 1 and label 2. So, then this is a factorial design with two factors, and in this case you have four experimental settings, independent experimental settings. One is when factor A is at label 1, B at label 1, that is 1 1, factor A at label 2, B at label 1, that is 2 1, factor A at label 1, B at label 2, that is 1 2, and then factor A and B both at level 2, that is 2 2. Otherwise also we write that this is low and this is high. So, 1 stands for A values, low value, and B high value. Similarly, this one for factor B, low and high value. For example, if factor A is temperature and we find that 15 degree centigrade temperature is low and 25 degree centigrade temperature is high, then we can put them as low, high or 1 2 instead of writing 15 and 25 degree centigrade. We can write like this, but more wide use is 1 2, low, high. Sometimes we use -1 and +1 also. This is also low is we write -1 and high we write +1. This is the notation is used. So, -1 and this will be +1. Suppose the that factor B is reaction time, then maybe reaction time, that is low means maybe 1 hour and high means maybe 3 hours. So, what is low and what is high, that will be determined by the expert, because the operators, the process expert, if it is a experiment related to any kind of process. Now, here it is a factorial design. This design is factorial design having two levels, each of the two factors A and B. So, there can be 3 factors, there can be 4 factors, and the label of the factors can be, every factor may be more than 2, and that there is no hard and fast rule that A will be with A and B or other factors will be having equal number of labels. Okay. So, if this is the case, then we have experimental settings or experimental and where we do the experimental experiment 1 2 3 4, and this is actually 1 2 1 2 3 and 4 giving like this. This is first setting, second setting, third setting, fourth setting. And now, keeping A 1 B 1 means A at low, B at low, you can run the experiment 1 time, 2 times, 3 times, n number of times. Then you will be getting response values depending on the replication 1 time, 2 time, 3 time or more number of times. So, what is this y 1 1, y 1 1 2, y 1 3, all these are y values here, response values when you run the experiment here. Or similarly this, similarly this, similarly this. So, but it can be something like this: A with 1 to A labels, B also 1 to B labels. Okay. So, there can be there can be 3 factors A with 1 2 A labels, B with 1 2 B labels, C with 1 2 C labels. Suppose if A equal to B equal to C equal to 2, then the experiment settings will be a cube. So, you have 8 points, 8 experimental settings 1 2 3 4 5 6 7 8 and here this is for simplification we have used this equal to 2, but suppose in this case suppose A equal to 3 and B equal to 4, then the things will be like this. Settings will be A 1 2 3, B 1 2 3 4, then your number of experimental runs will be here this 1 2 3, then 1 2 3 4, 1 2 3 4, 1 2 3. So, 1 2 3 4 5 6 7 8 9 10 11 12. So, experimental settings here is 12. Here experimental setting is equal to 8. So, these are known as treatment combination, experimental treatment combinations. So, all those are basically example of factorial experiments, and pictorial representation is possible when the number of labels as well as number of factors is 3 or 2, 3 or less. Otherwise, we have to use the tabular formulation. So, what we will discuss today, we will discuss this under these factorial experiments. So, what are the key concepts, and then what kind of data you will gather after experiment, and what are the hypotheses you will test here, and I will show you one example, that hypothetical example for factorial experiment with data. So, whatever may be the case, if you have 2 factors, 3 factors, you can have factor 2 factors, you can have 3 factors, you can have k number of factors, Okay. So, few important things are that one is when we have several factors, every factor affect the response y. So, y will be function of factors A, B, C, D, all those things. So, every factor might have influence on the observation y, as well as the factors may be correlated or they might have interaction effects on y. So, as a result, the one of the important concept is called main effect. Main effect means this is basically the effect of changing the every one factor from one level to another level, primarily from low to high. What will be the change in y? That change means mean change. Okay. So, change in mean of y, change in mean response when you change a factor from low to high, from factor from one level to another, For example, if A is having two levels, suppose what will be if you change from one level, that low level which we say minus, to high level which we may say plus. So, low to high, then there will be change in y. So, this will be y bar minus, this may be y bar plus. Then what is the change? Change in average is y bar plus minus y bar minus. This change is main effect. Another one will be the interaction effect. What is this interaction effect? It is something like this. Suppose you keep both the factors a and b at the same level, like 1 1 or 2 2, same level. If both low or both high, they are all same level, and they will be at different level. When a at low level, b will be at high level, b at low, a will be high level. Then what is the average change in mean responses when all of the factors are kept at that same level with respect to the factors are at different levels. So, that means the observation here and here will be averaged, and observation here and here also will be averaged. So, the average of y, this minus this, will give you the interaction effect. So, in that sense, if I want to show that mean main effect something like this, depending on whether it is a or b, but it is basically positive, the difference in mean when they are at high level, at low level. So, it can be then interaction effect, we can write like this: y bar may be both at high different level, and suppose I say different level minus y bar same level. So, that will give you interaction effects. So, another important thing is that then what will be the number of main effects? What will be the main effect, total number of main effects? It will be, if there are k factors, main effects will be k. For example, here 2 factors, so 2 main effects. What will be the interaction effects? Interaction effects will be k C 2. If there are 2 factors, then it will be 2 C 2 will be 1. Similarly, in this case 3 main effects, and then you have another concept that in interaction effects, one is two-way interactions, as there are 3 things, every 2 factor will be interacting and all 3 factor will be interacting simultaneously. So, 3-way interactions. So, 2-way interaction means 3 C 2, find out it will be 3, and 3-way interaction 3 C 3, it will be 1. So, effectively 3 plus 3 plus 1, 7 effect you have to estimate it, and here 3 effect you have to estimate. So, if you go for k number of factors, so main effect will be k, 2a will be k C 2, 3a will be k C 3. So, like this k C k, last will be 1. So, you will be a large number of effects that is to be estimated. Okay. So, in addition to this, please remember the replication will also be there in each experimental runs or experimental settings. Every treatment combination there will be different replicated experiments. So, in that case you will be having more than one y value at each experimental settings or at each treatment combination. you will be having n number of values. When we talk about averaging, we basically take sum of all including the replicated values and the other condition, whether it is at low or high or at same level or different level, and then we subtract. Okay. Let us see one example. So, here we have two factors, factor A and B, A at two levels, B at two levels. It is denoted by low and high for or minus or plus. So, we are interested to compute the main effects and interaction effects. So, what you require? You require what are the values of response variable when you conduct experiment keeping at the factors at different levels. So, when A at low and B at low, then the y value what you or response value you observe is 10, and here we are considering one replication, means single replicate n equal to 1. So, then when A at high, B at low, the response value is 30, and when A at low and B at high, response value is 40, and when both are at high level, response value is y value is 62. So, what we want? We want to compute the main effect. So, suppose we are interested to compute the main effect of A, factor A. In that case, what you do? You take the average of response when A at high minus average of response when A at low. So, this is denoted by A equal to y A plus minus A plus bar minus y A minus bar. Okay. So, then the value is 30 plus 62. You see, when A at high value irrespective of the presence of B, you consider when A at high, what are the y values? 30 and 62. So, 30 plus 62 by 2, because there are two observations 30 and 62. So, this is the average y A plus bar. Similarly, when A at low, that is 40 and 10, the average is 10 plus 40 by 2, the difference is giving you a value 21. This is what is the effect of A. What does it mean? If you change A from low to high, y change will be 21. Okay. So, or if I say that it is from minus to plus, means minus 1 to plus 1, the change is 21. In the same manner, you can compute B effect. So, for B effect, when B at high, the average will be 62 plus 40 by 2. When B at low, the average will be 30 plus 10 by 2. So, ultimately the difference is 31. It indicates that when you change B from minus 1 to plus 1 or low to high, the change in y will be 31 units. Now, come to the interaction AB here. You see what is there, AB. In AB case, so you are basically considering when they are at high same level minus they are at different levels. So, 62 plus 10 by 2, that is where they are the same levels, and then 40 plus 30 by 2 when at different levels. So, 40 plus 30 by 2. So, that difference is 1. Okay. So, this A and B, the value 21 and 31 and AB 1, these are the effect values. A and B are the main effect, AB is the interaction effect. If you see the values, you find that the AB values are quite high, but AB interaction is very low. So, it can be neglected, but later on we will see how to do the significant test of all those effects. So, that some of the effects will be neglected for further consideration. Now, here what happened, it is basically talking about, so you can see this graph, I can write this graph. So, the graph is response versus, suppose this side A and this side response. What is response? Response is y. So, a at low or minus to high or plus. Now, consider b at low. When b at low, a at low, the value is 10, y value is 10. When a high and b low, the value is 30. Suppose this is 30. Then if I join, I will get a line like this, which is b minus. That means this is a curve b at low, but you are changing a. Now, there will be similarly b plus curve. So, if this is 10, this is 30, let this is 40. When a at low, b at high, y response is 40, and when both are at high, that is 62. So, something like this. This is 62. You do this. So, this is B positive. Now, these two are more or less parallel, and we have seen the AB interaction effect is 1, which is also very less. So, if there is no interaction effect, you will find out that when you plot the response values for a particular factor and then keeping another factor at a particular level, you will get parallel lines. Suppose if there is another level for B, that means low, medium and high, then what will happen? You also get maybe similar another plot, which is this is low, this is medium and this one is B high. So, there will be parallel lines. So, there is no interaction effects. As we have seen that A, if you make it from low to high, the response is increasing, and that is why this slope is coming. When when there are interaction effects, what will happen? You see the next slide. In this case, again the same fact, both two factors, and you see that ultimately the response values are different here, and when you compute the main effect, A is 6, B is minus 14 and AB is minus 24. So, what does it mean? It means that A effect, if you change from low to high, then 6 units change in mean response. For B it is minus 14 units change, lowering, and for AB interaction, that combination will give you minus 24 units less. Now, if you this side A and this side response, and then what happened? It is with respect to B. So, when B at low, this is 30 and 60, and when B at high, 40 and 22. So, that means here when there is interaction, what is happening? When there is interaction, you will get a, suppose A low to high you are making. So, you will find out something like this, something like this. So, the response values, suppose this is B minus and this is B plus, they will interact, and then the AB value, that will be quite significant. In this case, it is minus 24, so it is a high value. Okay. So, so far then I have talked about two different factors, and they are having at two levels, minus and plus, and so we can say y is function of A and B, or in regression mode we can write it is x1 and x2. Then we can write down at this one is beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon. Now, is there any relation between the main effects and interaction effects and the regression parameter? This is a regression equation when x1 and x2 are purely independent IVs. But if x1 and x2 are x1 and x2 have interaction effects, what will happen? This y will become beta 0, beta 1 x1, beta 2 x2 plus beta 1 2 x1 x2 plus epsilon. So, if A is the main effect, then its corresponding regression effect is beta 1, B is another main effect, corresponding regression coefficient is beta 2, and then AB is interaction effect, corresponding regression coefficient is beta 1 2. Then what is the beta 0? Beta 0 is the intercept, this is the grand mean. So, grand mean is actually represented by beta 0. So, as you have seen that you have estimated A, B main effect as interaction effects, can we get an estimate for the regression coefficient? Interestingly, it is there. For example, if you take this case, A is 6, but what is this? When you are changing from minus to plus, so minus 1 means minus 1 to plus 1, you are making the change, that means 2 units change in A, 2 units change in A is represented by the effect change in A makes 6 units change in Y. So, but when we compute regression coefficient, that is 1 unit change in x1, what is the change in Y? So, that means if 1 unit change in Y, the x that will create, that means A by 2 unit change in Y. As a result, beta 1 will be A by 2, beta 2 will be B by 2 and beta 1 2 will be A B by 2. That is what we have given here. That is what is given here. So, and here beta 1 2 is very large, okay, this is minus 12. Then here you see when other one that beta 1 is 10.5 and beta 2 is 15.5, beta 1 2 is 0.5, all are positives. Okay. So, what will be the grand average here? 62 plus 40, 102 plus 40. So, 142 divided by 4, that what will be the that beta 0 value then for this case? For the first example, beta 0 will be 142 divided by 4. So, what is this? 4 into 3, 22, 5.35.4. What is beta 1 value? Beta 1 is 21 by 2, that is 10.5. Beta 2 will be 31 by 2, that is 15.5, and beta 1 2 will be 1 by 2, that is 0.5. Then what will be the resultant regression equation? So, resultant, okay, this is 35.5 maybe, okay. So, yes, 35.5, 4 into 5. So, see the slide, what happened in the first example, the regression equation will be y cap is the fitted y is 35.5 plus 10.5 x1, 15.5 x2 plus 0.5 x1 x2. Now, this as this value is very less, and later on if we find that that is not significant, then this can be a reduced equation will be like this. So, that means it is a linear regression plane, and you will when you plot x1 x2 versus y, you will find out a flat basically a surface like this. So, here what happened, x1 changing from -1 to +1, x2 changing from -1 to +1, then y changing from different values from y that 22. So, some value maybe 10 to whatever the range is available. So, this is known as response surface. Okay. Now, here in the right hand side contour plots given for that, mean contour is that equal contour is the basically joining the points having equal property. For example, if you join on all the points on the earth surface having equal altitude, that is from mean sea level, then this is a contour line. If you connect the cities with equal mean annual mean temperature, that is temperature contour line. In the same manner, here what happened, the contour line is, we are basically joining the lines, joining the points with equal number of same value of y for different values of x. Essentially, you may get, for this kind of, when there is no interaction effect, you will get this kind of lines. This is suppose x1 and this is x2 and these are all y values. So, these are all y values. This is suppose y1, this is y2. What does it mean? Suppose if I consider any point on this line is having a particular y value. Suppose if y is, this is 40, then all here also 40, here 40, here 40, everywhere 40. What does it mean? If I consider this point and then make a projection here, then x1 this may be 0, this is -1, this is +1. So, this is again -1, this may be your 0, this is your +1. And if I do like this and this may be 0, this is -1, this may be -0.2. Suppose if I take a point here, so this is again -0.2 and this may be 0.6. So, that means if x1 is, you have a range of for setting x1 and x2 or factor a and b. If you want y should be around 40, then this is the line, contour line, which gives you a range of x1 and x2, and so that you can set the machine or the process keeping different values of x1 and different values of x2. Whether that means from here to this, here this is the range for x1, and similarly this is the range for x1, and similarly you will find out the range for that -1 to +1, this big range, this range for x2. If you want y should be around 40, you choose any point here and corresponding x1, x2 will give you the upper parameter settings where you will fix. Suppose this is the line, suppose this one is 70 and your y is, this line is 70, your y is maximum is a higher the better case, then you will be interested to run the machine keeping x1 maybe 1, then y x2 will be something like this. Okay. So, this sense the response surface will be understood. Now, I will give you from example to generalization with a 2 factor case. So, the data representation for 2 factorial case will be factor A with A labels, factor B with B labels, then and if there are n replication, then your data set will be like this. And then what will be the statistical model? Statistical model will be something like this. We have y I for factor A, j for factor B and k for replication, and then this will be having a grand mean plus tau I, that is factor A effect, beta j factor B effect, plus tau beta I j, that is the interaction effect, plus epsilon I j k. So, this is the general observation, this is grand mean, this is our factor A effect, factor B effect, this is interaction AB effect, this is your error, and I stands from 1 to A, J stands from 1 to B, K 1 to N. This is known as fixed effect model. Fixed effect model. You may be interested in a mean model. If you are interested in a mean model, then what happened? The entire thing, this will be written as mu I j, and then y I j k will be mu I j plus epsilon I j k. This is known as mean model. So, if I say for two factorial experiment, what is the statistical model? Fixed effect model is this. What will be your role? Your role will be to estimate all the parameters, and then thereafter you test whether this this model is significantly contributing in explaining the wise variability or not. Okay. So, that we will see later on, and and accordingly we test certain amount of hypothesis anyhow. So, for the time being we just let us see the hypothesis also. So, what happened? What will be the hypothesis? Hypothesis will be whether the main effects are significant, individual main effects significant or not, individual interaction effects significant or not. In this case, we have two treatment, one is row treatment, another one is column treatment, that is factor A and factor B, and also we have interaction A B. So, what we are writing H0, that there is no difference between the treatment levels, row treatment levels, and H1 at least there is one difference. Similarly, for column treatment level there is no difference, H1 there is difference, and hypothesis regarding treatment interaction. So, there is the treatment effects are 0, interaction effects are 0 for all I j, at least one tau beta I j not equal to 0. So, these are the hypothesis. So, we are basically we want to test here three kinds of hypothesis, one for factor A, another for factor B, and another for interaction A B. So, if you have k number of factors, k factors, so how many tests you will be doing? For all main effects, k main effects, 2-way interaction effects, 3-way interaction effects. So, those many effects are there, all main and interaction effects including 2-way to multi-way, kth way interaction effect, all those effects, for all those effects you will be basically putting one hypothesis. If there are k factors, k hypothesis for main effects, and then Kc2 hypothesis for 2-way interaction effects, Kc3 hypothesis for 3-way interaction effect, like this you have to do. Okay. So, we will see one experiment in the next class, and all those things what we have discussed so far, how the factorial experiments is developed and all those things. Suppose if I consider this experiment that the shelf life of a perishable product is dependent on temperature and pressure under which it is stored. So, there are two controllable factors, temperature and pressure, which basically governs the shelf life. both both pressure and temperature are controllable with 3 levels each. So, low, medium, high and low, medium, high. These 3 levels are chosen within the operating zone. It is basically it must be in the operating zone. This define a factorial design with 2 factors pressure. This is a factorial design. Now, let us assume that you have done the experiment and basically you have seen what is actually happening in the store, and then suppose when it is temperature pressure at low level, low, then you have 4 replication, for low medium 4, for low high 4, similarly medium low 4. So, 4 replications. Then this is a factorial experiment with 2 factors, factor A at 3 levels, factor B at 3 levels, shelf life is the response variable and replication is 4, here the data is hypothetical. Okay. So, when you do factorial experiment, depending on the problem and depending on the number of controllable factors that is to be controlled and depending on the sample size requirement, you will be having the after experiment you will be having data similar to this. So, I hope you understand the factorial experiment and also you know what will be the statistical model for factorial experiment. In next class, we will be discussing on how to see that whether the model is able to explain the variability of the data using ANOVA, and then next to that we will see that how the different parameters of the model will be estimated, and followed by the residual analysis or the test of assumptions and other things. Thank you very much.